Hey everybody, thanks for joining. We're going to continue our study of limits. We're going to look at an informal description of a limit. What I want you to kind of take away from this statement here is the notation that when we decode this, we need to be writing. Okay? So the limit of a function. So LIM, of course, is the abbreviation. F of x is the function. This is all in the same line as x approaches c. I'm hoping with time I'll get better with this tool. Okay? All right. Now, limits can be found graphically, numerically, and analytically. So in this first example right here that we're going to look at, we're going to start with the graphical approach. So here we have, in this example, we have this function. It wants us to make a conjecture about the value of the limit as x approaches 0. Okay, as x coordinates become really close to 0. Now remember, it's not about being at x equals 0, although it's sometimes helpful to know what the functional value is at 0. Really the idea of a limit is not being at x equals 0. But like I said, it's sometimes very helpful, many times very helpful to know what is going on exactly at x equals 0. Alright, find a complete graph of the function near where x is 0. So if you want to take the time and maybe pause the video, whatever, and go to your calculator and type this into y1, or any open y equals register you have. When you type it into your calculator, you're going to observe some kind of graph that looks like this. Okay, and you're going to think, okay, that's nice and good. That's a nice exponential. Makes sense because we have the natural exponential function in this this equation here. However, we know better. As calculus students, we know that if x is 0, that we're dividing by 0, and that's never good. So why don't you take the time on your calculator, since you have this in, why don't you hit the trace key. When you press trace and then you press x equals 0, notice that there's no value for the y-coordinate. Okay, well what does that tell us? Even though we can't see it, it tells us, got to draw faster with this pen, it tells us that we have a point of discontinuity. We have a point discontinuity here. There's no y-coordinate when x is 0. And that makes sense. There's our graph. So we've got a complete graph of the function near where x is 0. Alright, use the trace feature on both sides of x equals 0 to find these limit questions. So look at question A. What's the limit of this function as x approaches 0 from the left? Okay, remember the negative sign here means it just gives direction. Okay, I can approach 0 from the left side of 0, the right hand side of 0, and here with the superscript we're approaching 0 from the left. Okay, well this is the left hand side of where this x coordinate is 0. Okay, so what we want to do is we want to approach 0 from the left. So, you know, all these x coordinates of these points right here, they're to the left of 0, but as I move in this way, my x coordinates are approaching 0. So that's, you know, what this statement means right here. Okay, so you're observing. So one at a time, slowly. Okay, as x gets closer and closer to 0 from the left, what do the y values appear to be approaching? Hopefully you're saying 1. So there you go. The point doesn't have to be there. My graph is going into 1. Okay, now let's look at the right-hand limit. As x approaches 0 from the right, so here's 0. I'm going to approach 0 from the right side of 0. I'm going to go back and approach the 0 from this side. Okay, what are the y values approaching? And hopefully you've taken the time on your trace feature, you know, to observe what the y's are doing as your x coordinates of points are getting closer and closer to 0. Hopefully you said 1. The left limit and the right limit are equal. Therefore, if these two values are the same, probably indicates a point discontinuity if there's not a point there. Okay, the limit of the function as x approaches 0, okay, is equal to 1. Okay, so we just found a limit graphically. This would be a good place probably before we go to the numerical and analytical approach for me to kind of come over here to the graph and let's kind of visit the functional value idea. So if I said what's the functional value, okay, at 0, I'm saying what's the y-coordinate that belongs to an x-coordinate of 0. Well, let's go back to the original function. Everywhere we see x, replace x with 0. E to the 0 is 1. 1 minus 1 is 0. So we end up with 0 over 0. Okay, well look at this form here. This form is what we call the indeterminate form. It's indeterminate. And when we arrive at this form, and we're talking about the context of a functional value, it's indeterminate. Okay, what we want to state is, okay, well, the functional value then is, well, it doesn't exist. There is no y-coordinate. You'll see it as undefined. You may see it as does not exist. Okay? The functional value does not exist, or you can say the functional value is undefined. I'll take either. Okay, but I think it's good to kind of stop here and observe what's going on. The functional value does not exist, but the limit does exist. Okay, because remember what that means. The limit means you're approaching 0 without ever having to be at x equals 0. I don't need a point, okay, with the limit idea with an x-coordinate of 0. I just need to be approaching. And does the graph suggest that it's going into the same location with or without that point being there? Think about the diner problem. When the diner burned. Okay. All right, so we've looked at the graphical approach to finding the limit. Okay, now let's look at the numerical approach. All right. So these are x-coordinates of points on the graph. You know, we've really kind of already done this when we've looked at the trace feature. And kind of think about on the graph where you would be if your x-coordinate's negative 0.1. If you're at negative 0.1, you're probably about right here. What's your y? Okay, and then according to the table, then I'm going to move into negative 0.01, which is really close to 0. So then I'm talking about being at this point right here. And then I'm moving even closer and closer. Okay. So I'm going to take turns putting all of these x-coordinates right here into the function. It's going to be 0.95163. .99502. 0.99950 and 0.99995. And I'm going to stop here for just a minute because I want you to notice these x values. These x values, okay, up until this point are approaching 0 from the left. So we have enough data to kind of make an observation, look at the y's. These y values are approaching 1. Okay. And if we kind of take a peek in down here at these questions, it's asking us, what's the limit of the function as x approaches 0 from the left? Well, that would be these values right here, and they are going into 1. Just observing these x values right here, 0.1 to 0.01 to 0.001, etc., those are also going into 0 just from the right. So I'm going to actually fill in this data table from the right-hand side. So what's the y value on the graph when the x is 0.1? When I move closer to 0 yet from the right, 1.00, I think it's 5017, 1.0005, and 1.0001. Okay, so down here when we're asked to use the data to answer this question as x approaches 0 from the right, the y's are also going to 1. So we can say, therefore, the limit of the function is 1. Okay, and remember that if I were to evaluate the function at 0, like I did up here, that I'm actually going to get undefined or does not exist. Okay, so the value does not exist. So I'm just going to kind of put that right here. There's not a built-in column for it, but I'll just put it right there. Okay? Okay, let's go ahead and try and do direct substitution. But you already know we've done this for the functional value. What's going to happen? We're going to get 0 over 0. Okay. All right, so what does that tell us? The first thing I'm always going to try is, okay, let me try and plug in that x value and see if I get a nice number. If I do, I'm done. I can continue on to another problem. If I don't get a nice number, then, well, I might have to come up with plan B, graphical approach, plan C, numerical approach. Okay. All right, so in this case, direct substitution gives us 0 over 0, indeterminate. What does that tell us? Well, it tells us that the functional value does not exist okay, at x equals 0, but it really doesn't reveal to us anything about the limit. In this case right here, we're just going to have to stop, okay, and we're going to have to abandon this approach and go to a graphical or a numerical approach, because there's nothing for us to do algebraically here. Now, in a few months, using L'Hopital's rule, another piece of calculus, we're going to be able to evaluate this limit analytically without having to look at it graphically or numerically. But for right now, we're kind of at a standstill until we gain more knowledge. Okay? So if you tried this first and you get to the indeterminate form and you don't see anything that can be done over here, like factoring, etc., anything algebraic, then you're going to have to just abandon and go to a graphical or numerical approach. You know, something interesting has to be happening at x equals 3, because if x were 3, I would be dividing by 0. Okay. So what we can do, actually, if you want to in this space, is we can kind of see what the functional value is, okay, at 3. So if I were to evaluate this function at 3, I'm going to get 0 over 0. So that tells us the function does not exist at 0. So I'm probably going to come up here and I'm going to put in or remove a point, try and show a little hole there. Okay. Might be able to erase that little line through there. I just haven't figured it out yet, but that'll come. Okay, so the function does not exist, is undefined. That doesn't necessarily mean our limit doesn't exist, and that's the question at hand here. Okay, but that is a complete graph. Use the trace feature. We know how to do that, so if you need to pause, you know, and use the trace feature to approach 3 from the left. This is the left side of 3. Monitor what the y's are approaching. I think you'll see that the y values are going into 6. Even though there's not a y coordinate when you trace and you plug in 3, you can still see that as you get closer and closer to 3 from the left that your y's are going into 6. Likewise, the right-hand limit, as you approach 3 from the right, is also 6. So the limit can exist, okay, even though the functional value does not exist. The point doesn't have to be there for the graph to be heading into a location. Again, the diner example, okay? All right. Okay, let's look at a different approach. Let's complete the table here. And as you can see, along your X row, we're approaching 3 from the left. And then again, we're approaching 3 from the right. We're going this way too. Okay? So I'm going to pause it. You might want to do the same thing and fill in your data table. Okay, now that the data table's been filled in, I'm so sorry it's sloppy. I'm going to try and get better. Use the values from the table to find. So let's say that this table was already generated for you. Okay, as x approaches 3 from the left, okay, my y values are going into 6. That's what the pattern suggests. My right limit is also 6. Therefore, the limit is 6. Because these two are the same. Okay? All right, let's try the direct substitution approach. All right, let's say we are given this initial limit problem, and to avoid graphing it or filling in a data table, maybe we can just go ahead and try and plug in 3. We've done this before, and we get 0 over 0. That's the indeterminate form. What that tells us is the functional value does not exist at x equals 3, but still that doesn't tell us anything about the limit. So we're going to take a look back at the function. Is it manageable with calculus or with algebra to maybe simplify this? Okay, and what we can do is I'm going to rewrite the limit statement, and then I'm going to take the function right here, and I'm going to factor the numerator. to sum and difference of like terms. Okay, and as you guys might notice, we have a common factor that we can cancel. And remember, when you cancel that common factor, the x-coordinate, or the x-value of that canceled factor, the x-value that makes it 0, if you will, the 0 of that common factor, I should say, is actually the x-coordinate of the point of discontinuity. So what I can do now is say this. I'm going to clean it up, and you should too here. I haven't lost the limit yet. Okay, all I've done is some algebraic work here, some canceling. Okay, with or without the parentheses. Okay, now try direct substitution again. Plug in 3. When you plug in 3, I lose the limit statement, and I get 6. So that confirms with what I did graphically and also numerically. So even though the function does not exist at x equals 3, the limit still exists because the graph's going into 6 without that point actually even having to be there. Okay.